Let's talk about aluminum. You touch this stuff every single day. It's lightweight, strong, and seems so simple. But the story of how it's actually made is one of incredible scientific challenge. We're talking extreme temperatures, massive amounts of energy, and even wrestling with invisible magnetic forces. I mean, just think about your day. It's right there in the sleek case of your smartphone. It's in the engine block and body panels of your car, making it lighter and way more efficient. It's in the giant airplanes we fly in, and it's the foil that wraps up your leftovers. Seriously, aluminum is pretty much the backbone of modern life. But here's the thing. Making this seemingly simple metal is anything but. The whole process is a story of brute force chemistry and physics on a scale that's just staggering. And it starts with a deceptively huge amount of raw material. So it all starts with this reddish, clay-like rock called bauxite ore. And you need a ton of it, somewhere between 4 and 6 tons actually. After a really complex refining process, all of that rock gets crushed and processed down to just 2 tons of a fine white powder called alumina. But get this, we're not even close to done. Right? All that work, all that rock, for just 1 ton of actual metal. That's a huge material cost. But the even bigger cost, the real secret ingredient, and the source of our first big scientific challenge, is a colossal amount of electricity. Okay, so let's go inside the heart of an aluminum smelter. This is the electrolytic cell, or what they just call a pot. This is where the magic happens. But trust me, it's less like a factory machine and more like a high-stakes scientific cauldron where chemistry gets pushed to its absolute limits. Now, the key to the whole thing is this really remarkable mineral called cryolite. You see, alumina itself melts at over 2,000 degrees Celsius, which is just insanely hot, not practical at all. But if you dissolve it in molten cryolite, boom, that temperature drops all the way down to a much more manageable, though still blistering, 960 degrees. Cryolite is basically the secret sauce that makes modern aluminum production possible. But getting this right requires some serious precision. This isn't just a simple soup, you know? It's an incredibly sensitive chemical recipe. If the temperature is off by just a few degrees, your efficiency just tanks. If the alumina concentration drops below about 2%, the whole reaction can short circuit in something they call an anode effect. Scientists even add these tiny pinches of other salts just to tweak the bath's conductivity and melting point. It's a constant, delicate balancing act. Okay, so we've got our electric cauldron bubbling away. But how do you get all that electricity into the mix? Well, you use something called an anode. And this brings us to our second major challenge, which is a wild one. The anode is literally designed to be destroyed. So check this out. A super powerful electric current flows through this massive carbon anode. As that electricity rips the oxygen away from the aluminum in the bath, those newly freed oxygen atoms are just irresistibly attracted to the carbon anode. And what happens when oxygen meets hot carbon? Poof! They react instantly, creating carbon dioxide gas. This means the very act of making aluminum consumes the anode, burning it away atom by atom. And of course, it gets more complicated. In the real world, these anodes aren't made of perfectly pure carbon. Nope, they're made from petroleum coke and pitch binders, and those contain trace amounts of other elements. All these impurities, sulfur, iron, you see them here, they can interfere with the reaction, acting like unwanted ingredients that just reduce the cell's overall efficiency. All right, let's move on to our final challenge, and honestly, this one is just bizarre. We've mastered the chemistry, we're managing the fact that our anode is basically on fire, but the sheer amount of electricity flowing through the pot creates this powerful, invisible force that threatens to tear the whole process apart. Yeah, there's a whole field of science for this. It's called magnetohydrodynamics, or MHD for short. And essentially, when you pump hundreds of thousands of amps of electricity through a conductive fluid, like, say, molten aluminum, you create an intense magnetic field. That field then pushes back on the molten metal, creating this crazy feedback loop of invisible forces. And this is where it gets super weird. Take a look at this computer model from a research paper. It shows what's happening to the molten aluminum. See that? The surface isn't flat at all. Those powerful MHD forces cause it to heave and slosh around, creating these invisible waves inside the pot. If those waves get too big and touch the anode sitting above it, boom, short circuit, a catastrophic failure for the cell. Just look at the difference the current makes here. At a lower line current of 124,000 amps, the metal surface heaves by about 5 centimeters. But when you crank it up to 206,000 amps, that heave more than doubles to 11 centimeters, creating much larger waves and dramatically increasing the risk of instability. Controlling these forces is a huge focus of modern smelter design. So as you can see, making aluminum is this massive challenge in material science, chemistry, and physics. It's also incredibly energy intensive and produces significant waste. But the cool part is, scientists and engineers are now tackling these problems head on, and they're turning these challenges into opportunities for some really incredible innovation. First up, the waste. For every ton of alumina, you get up to 1.5 tons of this bauxite residue, also known as red mud. Globally, that adds up to over 150 million tons of this highly alkaline waste produced every single year. Yeah. Figuring out ways to safely store or reuse it is a top priority. But what about the emissions from that burning anode? Well, this is where the next revolution is happening. Researchers are developing inert anodes made from ceramics or alloys that are not consumed during the reaction. Now think about what that means. Instead of oxygen reacting with carbon to make CO2, the main byproduct becomes pure, breathable oxygen. This would fundamentally change the environmental footprint of the entire industry. And finally, let's go back to that weird MHD problem. Remember how changing the electric current affects the cell stability? Well, engineers are getting so good at controlling that instability that they can now safely ramp the power consumption of a smelter up or down, effectively turning these massive energy consumers into giant batteries that can help stabilize a power grid running on intermittent renewables like solar and wind. And no, this isn't science fiction. As this research from 2023 points out, the goal is to create smelters that can flexibly adjust their power draw by as much as 25%. This allows them to soak up excess power when the sun is shining and the wind is blowing, and reduce demand when the grid is strained. Which leaves us with a pretty fascinating final thought. For over a century, aluminum has been defined by its voracious appetite for electricity. But by mastering the complex science inside that pot, we may be on the verge of a future where this energy hog becomes an essential and totally unexpected hero for creating a stable, renewable energy grid.